All right, and good morning. And if you're joining us live, welcome to our October 11th, 2025 edition of the At Home Planetarium Show. My name is Scott Harris. I'm your tour guide through the solar system today. And it is, again, a pleasure to have you with us either live or if you're watching this in a recorded version later, welcome to you too. And either way you're watching it, feel free to put comments or questions into the live chat feature and I'll be happy to answer those. If you would prefer, if you're watching it later, to email me at southernspacerocks@gmail.com. I also will be happy to answer you there. And so I'm going to get started this morning. As always, we're going to go over to our Stellarium program and take a look at the nighttime sky. And Stellarium here, I'm actually going to open up for you in real time today. And we'll hop over to it right now. And let's see if we can get that up here for you. All right, so it's going to, let's see if we've got the software working here. And here we are with our Stellarium Planetarium software, where we could just look out and at a made-up landscape here at the current time here on a bright Saturday morning in the southeast. And we're going to advance time here, and we're going to let time go by a little faster and a little faster, and we're going to go into the evening hours here. Actually, we're going to, let's see if I can get this into the so we're on the right date there at on the 11th, and we're approaching sunset, and so we're going to allow time to advance a little quicker here and get us all the way to sunset this evening. And we're going to talk today. Well, we're going to look at the highlights of the entire evening sky, do our tour through the solar system, but our focus today is on comets. And for a good reason. It is possible right now that if you have an unobstructed view of the western horizon as the sun is setting, you might be able to see with telescopes and binoculars and good cameras a comet that was just discovered this year that is called Comet Lemon 2025. It also has some other numerical designations that I won't worry about. But the big point is that it has a chance a little bit later this month, over the coming couple of weeks, to become what we call a naked eye comet, being visible without the aid of any type of binoculars or telescopes. And if that happens, we hope that it is really spectacular for you, that you can get to a dark sky and look out to the east. And so we're going to concentrate for a moment on where to look for that. And we're going to let the sun sink on down there. And as it does that here at about, we're approaching 7:30 or so this evening, and we'll let it go on there, and also we'll see Mercury and Mars there if you have a truly unobstructed view. There may be a little bit too much glare of the sun for you to really get much there, but here we are at just approaching 8 o'clock this evening. And I'm going to pause this here. And one of the first things you're going to see out on the western horizon that is going to get bright is Arcturus. And that is the brightest star in the constellation of Boötes the herdsman. Boötes is I see it as a kind of a kite in the sky. You might see it as other types of shapes. But what you want to look for is that bright red Arcturus. Above it, you may see a little bit of a diamond shape. And I'm going to put a little bit of the constellation lines here for you so that we can look up and see that. I often concentrate on this part here, making that diamond, and it coming down to Arcturus. Another way of making sure that you're looking at Arcturus is to go over to the northwestern part of the sky this time of year, and you'll find an asterism. That's a fancy word for star shape, called the Big Dipper. Everybody knows that, right? Well, just a little bit of things for those who don't know. This is not a constellation. It's an asterism. The constellation that it's part of course, is Ursa Major, the Great Bear. And if we look around toward the north, we might see the head of the bear. And the Dipper is the back and the tail of the bear. And my astronomer friends, as I always point out, often say that we can use the arc tail to create an arc in the sky over to the star Arcturus. Now, why is this particularly important right now? This is the region of the sky that you're going to be searching for those comets. And I'm going to go over to a little bit of a PowerPoint presentation here for you. And I'm going to stop sharing our night sky just for a moment. We'll be back to that. And we're going to go over and we're going to see first a very famous comet from back in 1996 and 97, and that is Hale-Bopp. And you see the beautiful ion tail here in the bluish and the dust tail that is reflecting in whiter light here. But the next slide that I have for you, if we can get that up, is a map of where to look for Comet 2025 Lemon. This technically, as I mentioned, 2025 A6 Lemon. And right now, we can come to October 11th, so we're right in here. And if you see that it is just below the body of Ursa Major, or right below the pan of the Dipper. So you're going to have to catch this at a time while the area beneath the Dipper is in your field of view. And as you saw, that may be a little tough for you right now, but over coming nights, if you could, again, want to get a very dark sky, no light pollution, not looking toward any cities, and you want to get a very unobstructed view of the western horizon as low as you can get. As we go into the next few weeks, though, we can get here in on the 23rd, so we're about 12 days away from that now. You can look in the center of that constellation of Boötes. So you're going to be looking up above Arcturus. And this is probably going to be the sweet spot of when people are going to really be outside and try to see this, if it is visible to the naked eye, and certainly to image it with your cameras. And I'm going to go away from that and come back to our night sky here for a moment. And so again, we can look out and see that region that we're going to aim for. Or again, right now, you're going to be right below the Dipper. And then over coming nights, you're going to look in that region between the back and the tail of the bear and come over to Arcturus. And really, you're going to be looking a little bit above that, sort of in the heart of Boötes. And I always like to show you, if you don't believe there's a herdsman there, we can employ some additional artwork here so that you get an idea of what the ancient astronomers saw in the sky, their imaginations. And we're going to come up a little higher in the sky right now. We actually see Draco the dragon. We see Hercules here battling the serpents. And as we look up toward the very top of the sky, you could find the bright stars of Vega and Altair and the slightly dimmer star of Deneb. If I take our both our artwork and our constellation markers away, we're left with this big triangle in the sky. That is what my astronomer friends call the summer triangle. It hangs on in the sky throughout the fall into the early part of the winter. But this is a great asterism to try to find that is composed there of the brightest stars in each of the three constellations. You may have seen there Vega and Lyra the Harp. Deneb is the tail feathers of Cygnus the Swan, and Altair is the eye of Aquila the Eagle. I like pointing out that Deneb can be used in a special way, that if you are in a light polluted sky and you're struggling to see where the Milky Way is, many cameras can image the Milky Way, the outer spiral arm of the Milky Way that we can see from Earth, without um, really, without worrying so much about the light pollution. I mean, if you're in a really heart of the city, it's tough, but you can be in a reasonably light polluted area and not be able to see the Milky Way naked eye. And if you know where to point your cameras, and particularly those that can give you a timed exposure shot, you can still get a pretty good image of the Milky Way. And to know where to aim, you want to find this triangle, and you want to find the Deneb and see the outstretched neck of the swan, and you may see the wings crossing it, but that neck is where you really want to look. That outstretched neck, you have to imagine that the swan is flying off to the south, and as it flies off toward the Antares, the red supergiant, the brightest star in Scorpius, that region of space where the swan is flying, that's where the Milky Way is. And in this view, this is a light polluted sky. You might just be able to make out the fuzziness of the Milky Way there. But that's going to come down to the horizon right in between Antares and this constellation over here that is Sagittarius. So you actually can go from Antares on the claw of the scorpion, swing around to the tail, and between the pointed tail and the tip of Sagittarius's arrow, that's where the Milky Way will pass. And at that point, you're actually looking straight in toward the center of our galaxy. So those of you who are interested in black holes, I always point out this is where you want to look to say you're looking toward that super massive black hole that hangs out at the center of the Milky Way that astronomers now call Sagittarius star, because it's technically in the constellation of Sagittarius. I'm going to swing around here to the southeast. Hopefully you have been looking off in that direction recently, particularly over the last week. You may have seen the moon over here, very close to Saturn, being very bright in the evening sky. And if you have binoculars or telescope, be sure to look at Saturn, see if you can catch a glimpse of the rings around it. They're a little tough right now in the and I'm just dynamically coming in here. They're not at a huge inclination. I'm going to stop that for us so we can not running away. And the rings are a little bit edge on right now, so a little tough to see. But you also want to look out beside Saturn if you do have a telescope and look for other bright little dots. One of those that you should be able to see is the large moon Titan. That is the one that actually has an atmosphere that is full of nitrogen, kind of like our own, except it doesn't have the oxygen we have. Instead, it has nitrogen combined with about 4 to 6% methane, or what we call natural gas. And it actually forms clouds and precipitation, rain and snow that falls down to the surface of Titan. And we have a spacecraft that hopefully will fly here in a few years to head out to Titan, and that is called Dragonfly. It's a big quadcopter drone about the size of a car that will be able to fly around in that atmosphere to explore the surface in detail. So I'm going to come back here to our horizon view. You might saw that Ceres is down here. Ceres is the small planet, dwarf planet that is in the asteroid belt. It's the largest occupant of that asteroid belt, but again is a planet in its own right. And we probably won't visit that on our tour of the solar system today. But if you have a good binoculars, telescope, and know exactly where to look here, that is an object that is bright enough to see if you know exactly where you're supposed to look. And we'll come around now to the northeast, and we'll see look back up at the summer triangle, and come back down and see if we can identify anything over here. I like pointing out that if we put the constellation markers back in, you may see a distinct W here. This is the Queen Cassiopeia. And if you can find Cassiopeia, or this K-looking feature here, the Perseus, you might, if you know your mythology, you might know that you're in the region of space where if you have the Queen you have the hero, you have the princess that the hero has to save, and that is Cassiopeia's daughter, Andromeda. And Andromeda is right over here, really composed of these 3 or 4 bright stars leading off from the great square of Pegasus. And she has an arm outstretched here, and if you look right at the end of that outstretched arm, you might be able to see a fuzzy patch, and that is her galaxy. That is the Andromeda Galaxy, our nearest spiral galaxy neighbor, at about 2.5 million light years away. It is that's the most distant object that we can see without the aid of binoculars and telescopes with our eyes. And of course, Perseus here, that is the great winged horse that Perseus used to help save Andromeda from the sea monster Cetus. And if you don't see the horse there in the sky, I'll go back and put in the markers for you. All right, so let's go now. I'm going to go over to our PowerPoint and talk to you about comets for a moment. And then we'll come back to our solar system view. And we're going to use a little extra software today called NASA Eyes. But let's go back, and again, now that we've shown you where to look for Comet 2025 A6 Lemon, keep that in mind over the coming couple of weeks. And let's just take a little bit of a view of comets. And back, several years ago now, in the middle of the pandemic, many of us had an opportunity to go out and see and image the comet Neowise. I thought I would share some of those memories with you this morning, and these are some of my photographs of Neowise. This one is faint here, but as you might be able to make out there, and this is above the Charlie Elliott Astronomy Field down at the Charlie Elliott Wildlife Management Area off of I-20 near Mansfield, Georgia. The Charlie Elliott Astronomy Club has its meetings there monthly, and has a field dedicated to reasonably dark sky viewing. This was a great place to capture some images, and the images here were taken with the aid of binoculars and camera together. And these are taken by telescopes by my friend Ed Albin, and from the Deer Lick Astronomy Village, a little bit farther east out I-20 from Atlanta near Augusta. And so these are the sort of images that people will be trying to get of Comet Lemon again over the next couple of weeks. We've also had spectacular comets that have been available for viewing from Earth over the last several decades. We haven't had the opportunity to have really many great ones like this, though, in the northern hemisphere. It seems like the southern hemisphere often gets these, I believe this is Kohoutek there, where you can see the tail structure out across the entire sky. Just a fabulous view. And just for those of you who don't know a lot about comets, I can I'll put up this graphic for you. And what you really are looking for with the comets are the bright areas. That is going to be the coma here, that is reflecting a lot of sunlight. And then these are icy objects, at least they're coated in ices that sublimate as they get close to the sun. They warm up, those ices are turned to gas and are expelled. As they do that, they also take a lot of solid dust, mineral matter, and expel it away from the coma as well. Now, buried inside that bright coma is, what we think is a little bit denser ice along with some rocky material, and that is the nucleus of the comet. And that's something very solid that we can go and have either hit or landed on in some cases. And that's the actual, the physical comet itself. But the coma is that envelope of gases and dust around it. And then the solar wind interacting with that coma creates these tails with charged particles. They're streaming away in the ion tail, and the dust mineral bits themselves streaming away. They have more mass to them, so they're going to be they're sort of droop down behind the comet relative to the sun, whereas the ion tail is directed almost directly away from the sun as the charged particles in the solar wind stream by and force these charged particles away opposite the direction of the sun. So we've had the opportunity with spacecraft to view the comas up close and the nuclei of a number of comets over the years, including looking at Comet Halley, that is very famous. We had the Giotto spacecraft with the European Space Agency was able to go and image that and see the jetting that occurs. And if I remember right, this is Comet Hartley over here. We'll take a little bit of a different view of that in a moment. One of the most well-studied comet nuclei, though, is from the comet we affectionately call 67P. We often leave it at that because the Russian astronomers that discovered this, it's a little difficult for some of us to pronounce. Churyumov, Gerasimenko is my best attempt without having it in front of me. But this was visited by the Rosetta spacecraft, and it actually had a little spacecraft along with it that was a lander called Philae, and it landed here, sort of landed and then tilted over, but still was able to get some great data about the processes that go on this comet. And you'll notice that it looks like a big dog bone, right? It looks like it has two parts to it with a bridge between them. And this is what we call a contact binary, and we see that many of the comets out there look like they might be some sort of contact binaries with material that is loosely bound from two different objects coming together, loosely bound by gravity. Where do comets come from? Well, they come from different places. Many of the what we call long period comets come from out in the Oort cloud. That is up to 100,000 astronomical units away. An astronomical unit, one astronomical unit, or 1 AU as we say, is the distance from Earth to the Sun, about 93 million miles. And so if you multiply that by 100,000, you get way out there, a quarter of the way to the nearest star, which is a little over 4 light years away with the Alpha, Proxima, Beta Centauri system. And that means that there's a lot that is influenced by the gravity of our sun. So that's what our solar system is. It's everything that's gravitationally bound to our star. And so there's a region out here that many of these long period comets come from. Icy bodies that can be disturbed and then sent into orbits that take them in crossing the plane of our planetary system, our near planetary system. And that's when we often get to see these beautiful long tails. But there are others too that come from about 20 to 50 AU in the Kuiper Belt. And there are others that actually come from areas between some of our gas giant planets. That there's a certain group of comets that come from the region close to Neptune, some that come from between Saturn and Uranus, even some that are called Jupiter family comets that are much closer into the interior of the solar system. And so those produce what we call short-term comets. Some of those can actually swing by us every couple to few years. And this shows you a little bit of what those short period comets are. They're actually defined as less than 200-year visits, and many of those are coming from inside of our planetary family here, as you see with Pluto's orbit out here. So these are what we call short period comets, and those greater than 200-year visits are our long period comets coming from deeper in the Kuiper Belt and the Oort cloud. As I mentioned, some of the ones that we visited here, Halley there with the Giotto one that's sort of near and dear to me is Deep Impact, because I was with the group along with Pete Schultz at the time, who was really involved in the collision of Deep Impact with Comet Tempel 1 to create a crater and actually use the ejecta from that crater to be able to tell something about the composition of the ices and the dust that's there. We've also visited Borelli, Wild 2, that is we visited with the Stardust spacecraft. Has been very important, those results, to understand the mineralogy of at least that comet, and speculate that it's similar to others. And then there's the Churyumov-Gerasimenko. Now I have it in front of me. I can say it a little bit better, that we visited with the Rosetta spacecraft. And this shows you Wild 2 up close, and it was visited by the Stardust, and it did something pretty spectacular, and that Stardust was able to fly through the tail and collect materials that then it brought back to Earth. And then here's another one of those contact binaries with Comet Hartley. And this is an animation of sort of how those form. Right? There's just particles. You can imagine ice and dust. They're just start off as two separate bodies, get very close to each other, and start influencing each other with their gravity, and then they form a sort of a bridge of material that then smooths out over time. So we don't think this is one object that then sort of pulls apart. We think these are two separate objects that are close to each other that then collide and get sculpted by their motion over time. This is a Tempel 1 I mentioned, and you see the collision there with the Deep Impact probe. That it actually had a camera that flew away so it could image this, but it basically had a big copper cylinder that it then sort of put in the way of this comet to be able to strike it. And one of the things that the camera system did on the object that was going to strike was it got better and better images as it got closer, and was able to transmit many of those. And we got to see that there was actually a dynamic surface here. There are some smooth young areas, some areas that are older with more craters. And the question, really was this a result of just are these new areas just from areas that recently had jetting on them and changed because of that, or are there more sort of stable geologic systems that exist on the nuclei of some of these bodies? Churyumov-Gerasimenko 67P, as I said, we were able to land on and get very up close pictures, and it's a whole world into itself, right? And one of the coolest things, sort of no pun intended, is that it essentially snows there, right? There are particles that are loosely bound that go up into space and then fall back, and so all of these icy particles are swarming around, and some of the camera systems really look like snowfall there on the surface. And Stardust, I was mentioning with Wild 2, the way we collected material from that was with aerogel, this stuff that's almost like air, that's just light and fluffy. And we put that into the inside a container that then flew through that tail, and as it flew through, very small particles traveling very fast hit the aerogel and then slowed down inside and were preserved. And so then the spacecraft brought that aerogel back, and it was investigated by a lot of the mineralogists and petrologists who I know, who then look at individual little particles and can tell the minerals that are there and what kind of rocks these are, and tell a lot about the early processes that were going on in our solar system. And many of these comets, we have reason to believe from Stardust and other technologies, other observations we've made, that these likely are carbonaceous materials, carbon and water-rich clays that, again, formed very early in the history of our solar system and have been under the influence of a lot of water, along with things like carbon dioxide, carbon monoxide, at these great distances from the sun in very cold regions of our solar system. But these are, kind of what we see as they're very similar to carbonaceous meteorites like this. This is a what's called a CI, carbonaceous chondrite, some of the most primitive materials that we have in our solar system. And in some of these carbonaceous meteorites, we actually find amino acids, hydrocarbons that ultimately are the same types of materials that go together to make proteins that go together to make living material. So we haven't found anything alive on these, but we do find the basic biochemistry, the basic biochemical building blocks that do lead on our planet to living material. And so this is I think recently that we've established that all the amino acid bases that we see in the in DNA are actually present in these meteorites. And this is what we think probably is at the heart of these comets. One of the most famous comets that, maybe apart from Comet Halley, was Shoemaker-Levy 9. And it's famous because it broke apart into the string of comets as it was influenced by the gravity of Jupiter, and then ultimately in the summer of 1994 crashed into Jupiter, leaving these large impact scars in the atmosphere. And other impacts with comets, likely with comets, we experience here on Earth. This is a big part of what I study. This is the devastation in Siberia in 1908 from the Tunguska explosion. This was likely a small comet or comet fragment that maybe just as small as 30, 40 meters across that blew up over the skies of Siberia in 1908, about 10 kilometers high. And so there's no crater, the heat didn't melt anything, but the shock wave traveling through the atmosphere hit the ground and knocked down trees over a very, very large area. And we have evidence of these, what we call airbursts. Some of these might be weak asteroids, but many of them also likely are icy bodies. And so we have many of these over the last few decades here shown. We know some of these, as I said, are asteroidal, like the Chelyabinsk in 2013. That's definitely an ordinary chondrite. There are a number of these that are asteroidal, but many of these likely are explosions of these icy bodies very, very high in the atmosphere. And one of those that maybe some people got to see between about 8,000 and 10,000 years ago in the deserts of the Atacama in Chile and southern Peru. I've studied here by glasses that occur in those areas. These glasses, these big, in some cases big chunks of glass, and smaller ones, spread out over many, many tens of kilometers, actually over 100 kilometers now. These, we believe, were produced by the detonation of a comet or a comet that had already broken into a number of pieces, coming in and sort of like Tunguska, blowing up high in the atmosphere, but rather than 10 kilometers up, maybe just 100 meters up or a couple of 100 meters up. That is close enough that then the heat from that hits the surface with enough energy to melt the sand and soil and create these glasses. But when we go into these glasses, my job was to look at the minerals that are there, and I found minerals that are, you can actually tie the way they form, their assemblages, to comets. Now, most of these minerals are minerals that can occur on Earth naturally. They are minerals that occur in meteorites of other types. But the issue here was not just, hey, they occur, but how they occur together. And some of the changes that had taken place, like these rims of a mineral called cubonite, right on the edge of this nickel-bearing iron sulfide. And other people have done work, even experimental work here on Earth, to show the conditions for these assemblages to form, and almost all of them required having a lot of water. That you'd have to have something that had, off the planet, that had a lot of water at certain temperatures. And really, since we know these are not coming from Earth or from Mars, the only thing left are comets. And so it makes sense that if this weak comet came in, that it might be something that would break up easily and explode above the surface rather than hitting and making a large crater. So I'm going to come back now to our open space software that we use to tour the solar system. And I'm going to have to make sure I'm in the view here that where I can see. And I'm going to start off today with a little bit of a unique view. We are looking at our solar system sort of from afar. And just checking one thing here. And this artificial sphere that I have put around it, that artificial sphere is denoting where the Oort cloud is. This is, as they say, the Oort sphere. And so in the middle of that is our sun and our planetary family. And so we're going to come through the edges of the Oort sphere, and we're going to enter that region of space about 20 to 50 AU away from the sun. That is the Kuiper belt. The inner edge of that Kuiper belt is marked by the orbit of Pluto, which is just outside the orbit of Neptune here, that's in the brighter blue. You see the orbit of Uranus there in the aqua color, Saturn in yellow, Jupiter in pink, and then the inner terrestrial planets closer to the center there. And let's go ahead, and since we're out here on the edge of the Kuiper belt, we can visit Pluto and Charon, two of my favorite planets. Charon I actually am very fond of, because before the New Horizons spacecraft visited the Pluto system back in 2015, we had a lot of speculation about what we would find with Pluto. And it was a surprise in how geologically active it is. But for all the debates you could have about Pluto and what you could claim to say, well, I thought this or thought that, no one, if anyone told you that they knew that Charon was as complex as it turned out to be, then they were simply lying. And so we'll take a look first at Pluto. One of the fun things about the Pluto is, as you hopefully know, it was named for the Roman god of the underworld. But it's interesting that this bright patch of ice often looks a bit like the head of another Pluto, and that is Pluto, the animated dog from Disney. And one of the things I can do with our open space software is I can look here at the shading and turn the natural shading from the sun off, because that's set, the shading here is set for actually right now. If you had been on Pluto, that's the Pluto that you would see, but not now. Now I've turned the shading off, so I've illuminated all of the surface that New Horizons was able to image in its 6.5 hour flyby. And now we see a little bit of that dog's head here. This patch is Sputnik Planitia. It is a large patch of largely nitrogen ice filling what we believe is a large impact basin. And there seems to be still warm, slushy ice underneath this, rising and falling in convection cells, convection currents, to create this polygonal terrain on the surface. Imagine like a lava lamp, but of slushy antifreeze underneath. That slushy antifreeze, in areas along the edge of Sputnik Planitia appears to erupt out and create cryovolcanoes, ice geysers, even with icy lava flows. And some of those, there's one mountain here called, for those Star Trek fans, there's Picard, actually named for a famous explorer here on Earth. Features on Pluto are named for great explorers of reality, including spacecraft explorers like Sputnik being the first artificial satellite to launch. But Charon, on the other hand, its features, everything from its craters to its plains to its mountains, are named for explorers of science fiction. And so if I can get that in there, we'll go take a closer look at Charon. And we see here it's this area called informally Mordor, for the Lord of the Rings. This patch of dark material is material either erupted or ejected off of Pluto that comes to rest here at the North Pole of Charon. We see bright craters here. Some of these bright craters have ejecta from them that contain substances such as ammonia, but most of the surface here is water ice. And that water ice, we think in some places, actually flows in some features that may be more akin to glaciers than lava flows, but many people propose that these are cryovolcanoes that produce some of the wrinkled terrains that you see. And as I mentioned, those explorers, if I come back here and look around the edges of the North Pole, one of the prominent craters that we find here is Dorothy. Now, is Dorothy an explorer? Well, that's Dorothy Gale of The Wizard of Oz. So, yeah, it's sort of the fictional explorer, right? All right, so let's just go ahead and take a look in our outer solar system today. We're going to ignore our inner solar system because I'm going to go back to comets here at the end. Let's take a look at Neptune for a moment. And Neptune we'll see is one of our gas giants. So many people now say, oh, it's an ice giant. Well, yes, but it's still one of our gas giants. All four of our gas giants have, most of their composition is gaseous hydrogen, along with helium. The reason it has this brilliant blue color is that methane ice crystals in the upper atmosphere, frozen against space, at this distance from the sun, are at the right temperature that they scatter the light from the sun to these blue wavelengths. There's some other reasons that happens too, but it largely has to do with the temperature that the methane is at, along with some of the dynamics that are occurring in the upper atmosphere of Neptune. And we do see some wispy white areas, the storms. There's also the dark spot that I believe is obscured in the shadowing here that represent large cyclonic storms, like you also see on Saturn and Jupiter. Around Neptune, there are a number of moons, but one that's special, one that really is a planet in its own right, and that is Triton. Triton is intriguing for many reasons, including the fact that it goes around Neptune the, quote, wrong way. It goes around clockwise rather than counterclockwise, which is an indication that it had to have been captured. So this was a Pluto-like object that was captured at some point by Neptune's gravity. And this is also the first place that we ever saw evidence of cryovolcanism, at least knowing it was cryovolcanism on another world. And this was done by the Voyager 2 spacecraft in 1989, flying by and seeing evidence of ice geysers that were on its surface. Um, we'll go to Uranus now. Uranus is also a blue world, and again, that largely has to do with methane in its upper atmosphere. It's a little warmer, right? It's closer to the sun, so the methane behaves a little differently. And around it are, again, a number of moons, but 5 of those are really special in that they are differentiated, and they're, for planetary geologists, they're really small planets in their own right. They all are tilted over close to 90 degrees to the plane of the rest of the solar system. And so this is one of the lines of evidence that we have that this Uranus was struck by something large early in its history that caused the entire system to tilt over on its side. And let's go now to Saturn. The last couple of weeks I've flown by Saturn, but not gone into a lot of detail with its moons. And since we're concentrating on icy worlds today, maybe I'll do that. As we look at Saturn, we see there are many moons. It's out to nearly 200 or so that are officially cataloged. But 7 of these are special. And you see their orbits there going from Mimas near the very, very close to the rings all the way out to Iapetus. And the rings are about 100,000 kilometers across from all the way going through Saturn. But despite that large diameter, they are only a few kilometers thick. So very, very thin, composed of icy materials that apparently came to be around 400 million years ago. They haven't always been there. And some materials, icy materials, were disrupted by its gravity and produced those rings, and they are being consumed by the cloud tops of Saturn as we speak. And they won't always be there unless something else comes in and is disrupted and creates new rings. Although there may be some thin wispy rings that are being fed by something not breaking up, but by eruptions of material off of nearby Enceladus. And if we visit Enceladus, we see a really tiny planet, but it is extremely geologically active. And one of the ways that you can recognize that immediately is it has a very young surface, not many craters. That indicates that some processes have renewed this surface over time. And we might have looked at something like this and wondered, well, how long is a long time? Was this resurfaced 1 billion years ago or yesterday? Well, fortunately, when the Cassini spacecraft was flying by and looked back in the direction of the sun, it saw huge jets of material going up above the surface from near the south pole of this world. And we determined that those are ice volcanoes, ice geysers shooting crystals of water ice along with some other more exotic chemistry out into space. And because that indicates there likely is a subsurface ocean or at least a slush beneath this with certain hydrocarbon chemistry, this is a place where many speculate that if we're going to find currently living bacteria, simple organisms off our own world, this may be our best bet. So there are a number of missions that are being planned. Nothing certain yet, but a number of really good mission plans are being put together for future visits to this world with the instruments to see if there might be any evidence of bacteria living on the surface or beneath those ices. And as I mentioned before, we have the spacecraft called Dragonfly that is planned, is being built. Hopefully everything stays on course for its flight in just a few years here. to go out to Titan. And this is not the view of Titan you would see if you were really approaching it. You would see a world shrouded in an orange cloud, that orange cloud from the methane that is prevalent there, again about 4 to 6% of its atmosphere. But the other 96% is nitrogen. And so many people think that the chemistry of this world was very similar to what Earth may have had in its very early days, 4.5 billion years ago. And here we're seeing through the clouds using radar. And we see some impact craters. This is a large impact structure, but you notice there aren't many of them, meaning that this surface is young. And so what's keeping it young? Well, lots of things. As we look carefully at these areas around the equator, we notice that there are features that look a little bit like river channels, dendritic stream patterns. So it was speculated about, are these actual liquids moving along? It turns out they likely were liquids, but not liquids that were there very long. Think of this like flash floods in a desert. The methane here acts like water. It condenses and forms clouds. The clouds rain and snow onto the surface, flow, and then evaporate again. And so in desert environments, you have very rapid precipitation followed by pretty rapid evaporation. And that's what tends to happen to the methane at the equator. Near the poles, though, we see dark, smooth areas. That's what those are in radar. They're dark and smooth. So they don't have to be a liquid. But near the poles, we see some of these dark areas that we have reason to believe still are liquid. So these are like lakes of methane and a few other hydrocarbons. So we're really looking forward to the Dragonfly flight out here coming up soon. So I'm going to take you to end today back to another type of view. And we're going to use the NASA EYES program. And I'm going to come over to what's called EYES on the solar system. And what I'm focusing on here, since the topic for the day was comets, a lot of attention is being paid to this comet called 3I Atlas that was discovered earlier this year. And if you have been following that, then you know that 3I Atlas is weird. It is one of these class of objects now that we have found a few of over the last few years. That is called an interstellar comet. It is not something that can go out to the Oort cloud and come back. This is on a hyperbolic orbit that is so fast. Its velocity along its orbit is so fast, it cannot have originated inside our solar system. So this was coming from somewhere else. And we don't have close-up images. There's an artistic version if you use this, which is just kind of made up. But we do have images now of it with its tails, and it also, I think I heard yesterday, has an antitail now. Antitails are material that are they're large dust grains that are falling off the coma and are falling off the nucleus and being part of the or falling outside the coma, away from the dust and ion trails. And they're always going to be opposite the direction of the ones that are being pushed by the solar wind, so that's why it's called an anti-tail. There is a tail now. For a while, it was said, oh, it doesn't have a tail, so it's strange. No, it has a tail. So these are icy materials that are sublimating from the heat from our sun, and they're being pushed away, just like other comets, by our solar wind. There may be some interesting things with its chemistry. The big thing is, where did it come from? What solar system did it originate in? And those things are trying to be figured out. It was imaged by some of our spacecraft at Mars just a couple weeks ago. And if we look at where it's headed, our next big opportunity to get data from this is because it's headed sort of crossing the orbit of Mars, will cross the orbit of Mars twice. And in doing that, it will be sort of in an area here relative to Europa Clipper, which is our spacecraft on its way out to Jupiter. There's been talk about trying to get some of its instruments to be turned on to observe Comet 3I Atlas as it passes through this region of space. And ultimately, it's going to pass by pretty close proximity to Jupiter as it goes back out of our solar system. And we have the spacecraft Juno that is operational there and might be reconfigured not only to image the comet from afar, but possibly could be repurposed to go and chase it for a little distance. So we're kind of waiting, to see if that really those options come to fruition or not. While I'm here, though, we can actually look at some of the other comments here. Halley, if you ever wonder where it's at, you can go and find it here with this NASA EYES program. And that's just really an artist rendition based on the Giotto data. But if we look at its track, we can find that it currently is out between, let's see, that's a live view there. So it's very inclined, as you see, so it's actually below the plane of the solar system, but in distance from the sun, it's sort of out there in that Uranus to Neptune distance, and it will be back here in 2000 and so 76 years from 86. So what's that? Around 2060 or so, and you can look at other comets as well, as you saw there. If we look at where 67P is, that's a Jupiter family comet, and we find that it is right there. It goes out very close to the orbit of Jupiter. Now, while I'm here, I want to visit one last place today that I normally don't get to visit in the Open Space program, and that is one of our other small bodies. And I know we're focusing on the comets, but I do want to take a quick look here at the asteroid Vesta, which is really one of these small planets. It's out the second largest occupant of the asteroid belt. And it is differentiated in much way that terrestrial planets are, in having, we believe, an iron-nickel core. There are basaltic lavas on the surface. I think this was a very dynamic world, and we have pieces of it in our meteorite collection called the HED meteorites. And they are igneous rocks that show us that this was a magmatic world at one point. And you might notice that if I drew a line out away from it in the circle, I can make a full sphere. And so this really was a spherical world, again, a little planet, but it got hit. And the reason we think we have so many of those HED meteorites is because one or maybe two collisions created two enormous basins. There's really the one that you see prominently with this huge mountain. It's called Rhea Silvia. That collision, you would think, liberated a huge amount of material that then some of which has found its way into Earth-crossing orbits, and we get as these meteorites. So that's where I'm going to end today. Again, if you are watching this in a recorded later and have any questions, feel free to put those into the live chat feature or to email me at southernspacerocks@gmail.com, and I'll be happy to answer. So thanks for being with me today. We will be here again in every week. We will have this program, although the next date I'm working out, because I will be coming up at the next week at the Geological Society of America meeting in San Antonio, giving 2 talks on impact structures. and also co-leading a field trip of impact structures in West Texas. So hopefully we'll be able to share some of that live for you from the field in the coming weeks. So thank you very much for being here again. Have a wonderful weekend.